Your sets are Saturday.
Nice.
1 to 2 p.m., right?
Yep.
All right. Dozen. They're to worry about it. They're ready for you.
Sweet, thanks. All right, we're up and recording, so it's time to go. That's right, it's past 7:30. All right, so we finished off yesterday going through all of the formulas, and I said today we'd put it all together. And we will. So, all right, so we're going to solve this problem right here. And there is if you follow this procedure, you will do just fine. And so we'll just do one by one. So the first thing I want to solve for, because this is an RCL circuit, for those of you who don't remember, so RCL or RLC, which means it has resistance and capacitance and inductance. So it has all three elements. So 440 volts, 60 hertz. We had this written down yesterday. So the first thing I want to do is I want to solve for X of L. And X of L is 2 pi frequency inductance, 2 pi FL. 2 pi FL. Are we with me so far?
Yes.
All right, so we're just going to plug in the numbers. X of L equals 2 times pi times the frequency, which is 60. Now be careful when you're looking at stuff, you know, if it's got 60 kilohertz or picofarads or microfarads, make sure you get that in there because that's a part of the number, right? Times the inductance, which is 3.5 henries, 3.5. So we could plug that all in our calculator, all in one shot. 2 times pi times 60 times 3.5 equals, so X of L equals, what do you got? 1,319. Now let's round properly. So my calculator is 0.468915. What do you want to call it?
47.
Well, you'd either go 0.5 or 0.47 or 0.469. Figure out what you want to do. We can go 2 decimal on this. We can go 0.47. 0.47 what? Ohms. Okay, X of L. All right. Then we're going to solve for X of C. All right, so X of C is almost the same. 2 pi FC, but it's the inverse, 1 over. So X of C equals 1 over 2 times pi times 60 times, he said, be careful with this, so that's 12 to the negative micro times 10 to the negative 6 is correct. So you can either put that in your calculator as EE negative 6 or convert it now, however you want to do it. Let's see. 2 times pi times 60 times so I've got X of C equals 1 over 0.00452389, on and on and on. I was going to say, I've never really thought about saving stuff. I wish you could do 1 over answer. I'm not sure how to do that on here. There it is. I see it. So you just do x minus 1 Second answer equals. That did not work. What's that?
What do you do?
I should have second answer on here,
Yeah,
but
when you do the answer and then x minus 1. Because I got 221.048.
I got it. So, what'd you end up getting?
221.049.
So that over so equals, I have 22.049, no, 221.049
Yeah.
is what I have. Got that? Ohms. All right. Next thing I would want to do is solve for x total. So you're writing these down, right, in this fashion. So first thing is x of L, and the second thing is x of C. Then third thing I want x total. X total is x of L minus x of C. So you have x total equals 1319.47 minus 221.049. And I get x total equals, what do you get? 1098.421. Is this circuit capacitive or inductive? Why is it inductive? Because xt, first of all, because xt is a positive number, and xt is positive because x of L is bigger than x. C.
Can you say that again?
Okay, is the circuit inductive or capacitive?
It's an inductive.
So another way to phrase that, is there more inductive reactance or is there more capacitive reactance? Well, all we have to do is look at x of L and x of C. Which one's bigger? That means it is inductive. Also, x total is a positive number. Because if xc was larger, and if x of c was 2,221, so 1319 minus 2,000 would give us a negative number, right? Then that would mean it was more capacitive. But as it stands, it is more inductive. Okay.
Can we go back to the x of C?
X of c.
Calculate the number,
Yep.
bottom number?
How did I get the bottom number?
Yeah.
So it's 1 divided by 0.00452.
The top in the calculator, like the 2 times 5 times 60 times 12.
Right there?
Middle one.
Right here?
Because it's in micro.
Because
12 times 10 to the minus
because remember it's 12 F microfarads.
Yeah.
So 12 microfarads is 12 times 10 to the negative 6, which is like saying 12, 1, 2, 3, 4, 5, 6. Right? Just like when we talked. So we haven't done a lot with micro, but it's something you have to get used to. This number here is going to either be a micro or a pico. So if it's pico, if that would have been 12 picofarads, that is like saying 12 times 10 to the negative 12. So I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you really want to get used to using that EE function on your calculator, or you're going to be off by 1 0, and right there, the rest of your answers are all wrong. And at that point, you're going to fail every single question on here. So to look at that again, I would have said, so we have 1 over 2 times pi times 60 times 12 microfarads, right? UF, which is the same thing as times 12, which is times 10 to the negative 6, which is like 12 EE minus 6 on your calculator. Remember how to do that? So it's 2 times the pi key times 60 times 12 second function EE, the negative, not minus, 6 equals, I think I screwed something up. 2, I don't think I cleared my calculator. 2 times pi times 60 times 12 second EE negative 6 equals, yeah, I didn't. So all of that right there should be 1 over 0.0. I lost them. You getting it?
I got that one, yeah.
Okay, you got it now? I'll just finish the 0042 or 452, and so second, oops, answer. Okay. So you get that right there. We got the 0042 whatever. Then hit second answer, which is the minus key down the bottom, and then the x minus 1 key and equals, and you should get 221.048. All right, so we've got, first we got x of L, then we got x of C, then we got x total. So all right, yeah.
What's the unit of measure for x total? Is it still ohms?
Still ohms because it's ohms, so we'll make that ohms. Get rid of some of this. Back to here. All right, what's next? Let's go number 4. Let's find Z. Impedance. Z, if you remember Z, that's our Pythagorean theorem. So that is R squared plus X total.
X total squared?
Squared, yes. You can also, like I said, do Z equals R squared plus XT minus XC squared. Well, if we take a look at what I just did here, what
XC minus XC?
XL, yeah, sorry. XL. This right here is the formula for XT. It's right there. So you're just skipping a step. But if somebody asks you what X of T is, you're like, I don't know, I didn't. I bypassed it. So that's a bad thing. You have to go back anyway. All right, so Z equals the square root of R squared, which was 500. So 500 squared plus X total squared. X total squared is 1098.421 squared. So we can do that. Like I said, I think you can do the whole thing in one shot. Although I'm not. I'm going to do 500 x squared plus 1098.421 x squared equals, so I get Z equals the square root of 1456528.693. And then I should be able to go second answers, no. Square root, second answer, close parentheses, equals, if we get the right thing. What'd you guys get?
1206.67.
So Z equals 1206.87. You want to call it that? I got 867, which is also 87.
Got it.
All right. Looking good there. So now we got Z. Everybody got Z?
Where'd you get the resistance? Where'd the 500?
From the resistor.
It's given. Yeah.
From the ohm.
Right there.
500.
What's that?
Okay.
Okay, good. Glad to hear it. All right, what are we going to do next? Let me see. Let's go. So number 5. The next thing I want to do is current flow. So we're going to do I total, which is the I for the whole thing since it's a series circuit, equals E divided by Z. So I total equals, what is E?
440 volts.
440. Where did I get that number? It's a given. Divided by Z, which we just got, which will be 1206.87. So I total equals
0.3645, so 0.365.
0.365 what? Amps.
Current total.
All right. I should have left myself some more room right here, so I'm going to redraw that.
So what is, can you go back to that real fast?
Yep. I'm gonna go back real slow too.
Thank you.
All right. Everybody's with me?
Mm-hmm.
We're not in a rush here. All right. But I should have made it a nicer drawing. So I can do E-I-R. I'll just do it this way. There.
What's the unit of measure for Z again?
It is
Ohm.
it is a derivative, so it's impedance, so it's like resistance, so it's ohms. Yes.
When we draw these out for like assignments and stuff, never mind, I was gonna ask, do we just do like EIR for all of them?
Like that?
Yeah.
Yeah. All right. So this was here 440. This is 60 hertz. Do we know anything else? Oh yeah. So we know. Oops, we'll leave it in red. So X of L is, which is R, which is X of L. 1319.
Yeah, 0.47.
Thank you. And this one was 221.
1.049.
All right, and we just got the I, which is,
0.365 amps.
so how much was it here?
0.365.
Oh, and this is 500. 0.365, 0.365. All right. So now we can solve for the voltage drop of R, L, and C. So E of R, this is going to blow your mind. It's EIR, so E is I times R. So E is 0.365 times 500 equals 182.5. 182.5 volts. E of L is 0.365 times 1319.47 equals 481.61 volts. All right. Then E of C. Well, I screwed something up. 0.365 times 221.049 equals 80.68. All right. That's not so hard. Well, now let's take a look at this. What do we got left? Resistance, which is?
U for I.
All right, so we got 440 divided by 0.365 equals 1205.48 ohms. All right, let's check everything out. All right, so 182 plus 481 plus 80 should equal? Uh-oh. 500 plus 1300 plus 221 equals?
No.
We got a problem. What's our problem? Ohm's law all fell apart, didn't it?
Yep.
Well, as I mentioned a day or so ago, we were going to get to this point, and it's going to be like, uh-oh, it doesn't work. These are vector sums. So if you remember in our notes, we talked about the resistance. It's not really resistance. It's not really resistance. It's X of L and X of C, which is like resistance to us, but because of phase shift and the way it calculates out, it doesn't work out to this. And so we don't really get this R total. There is no such thing. We call it Z impedance. So what was my impedance, by the way?
1206.7.
1206, was it?
Yeah, 0.87.
Well, look at that. It came out right about right. So I don't know if I ever noticed that. So because that works out here. So I guess to tell you that, don't worry about Z. I guess you can calculate it out there and get Z. But these aren't going to add up, and those aren't going to add up because of phase shifts. Because it's happening at different times. Well, then you want me to explain how do you get 481 out of 440? I don't know how to explain that one. It is what it is, right? Sometimes things are like, well, okay, I did what I'm supposed to do, and I don't totally understand this at this point, but I'm okay. So next thing we want to do is do our powers. So solve for power. So power. What number am I on here? 6. Okay, so the sixth thing I'm going to do. Oh, 6 might have been solve for E total, E of 1, E of L, and E of C. So that's what we did there for 6. 7 is power. We're going to do true power. True power, which is going to be, true power is going to equal, that's in volt amps, which is going to be equals I squared times R. So volt amps equals I squared is I is 0.365 times R, which is 500. Oops, that's not volt amps. I'm sorry. Made a mistake. It's just power true power. So true power, TP, true power. My bad. True power equals
I squared times
66.61.
6.25.
Ah, we can go 6.61 watts. Everybody got that?
And then that's the true power of the whole circuit.
Yep. Power apparent, which is volt amps, equals I squared times Z. So if we notice the two things, true power is based upon the true resistance, and power apparent is based upon the impedance, which is all things considered. So power apparent equals I squared, 0.365 squared, times Z, which was 1206.87. Power apparent equals
160.7.
he says 160.78. 160.79 because the next number is a 5, so we got to round up properly. 79 volt amps. Volt amps. This is pretty easy so far, huh? Just plugging in numbers here. 9. It's not like I'm going to ask you to write a paragraph. Well, explain to me the power apparent.
Don't do it.
Number 9. I want the power factor. Pucker factor. Remember, power factor is going to be a number between 0 and 1 that's going to tell me how good the circuit is. Power factor equals power true divided by power apparent. So the power factor equals power true, which is 6666.61 from above, divided by 160.79. So the power factor is,
0.414.
he says 0.414. If it is 0, that is a reactive circuit. If it is a 1, that is resistive. So purely resistive, purely reactive. So it's a little towards the reactive side, isn't it? Okay. Well, we could analyze that if we look up above and say, well, we had 500 versus 13 versus 221. So I'd say that's, getting a little bit over towards the reactive side. All right. Now
Is PF measured in anything, or is it just?
it's a ratio.
It's just 0.414.
0.414. Now we need, and I think this is the last thing, if I'm not mistaken, is the phase angle. What's this, number 9?
10.
10. Phase angle. Yeah. Phase angle. All right, so phase angle, we need to have our SOHCAHTOA, so that's S equals opposite over hypotenuse. C equals cosine equals adjacent. We'll just put A for adjacent, so everybody can remember that, over hypotenuse. And the tangent, which is opposite over adjacent. All right, so we've got that. That's our formula that we need to know. And we can draw out the circuit. So we had this, and we had this. So this is going to be my X total. We can do it this way. X total was how much?
1098.421.
421. And my resistance is 500.
1,205.48. What is the total?
Just the resistance.
Oh, okay.
Because remember, this is always resistance, and this is always the reactance, either XT or X. Well, it's XT. Sorry. So all right. So then I'm going to make this go up more. Doesn't have to be right, but yeah.
Are we taking the absolute value of x is t, or if it's negative, do we still put it in a negative?
Absolute value.
Okay.
Otherwise, it'd be kind of weird, wouldn't it? It just is down below. So we want this angle right there. That's my phase angle. And so the phase angle is going to be, what the hell notes I got written down here? Oh, I see. I have some weird notes here. I'm like, those numbers don't match up. But they don't, because it was a long way around or something. Okay. How you want to do it? You want to use the Sine, cosine, or tangent?
Tangent.
Well, and we know, well, here, and we also have the hypotenuse, which is z. And z is, I don't have it in front of me, 1206.87. So I've got z, I got this over here, x, I can use any one of them. You choose.
Tangent.
Tangent. He says tangent. He wants to go off on tangent over here. So the tangent, arctangent, really. So it's what do I want to say? It's arctangent, or it's actually t minus 1. So the angle of theta equals the opposite and the opposite. So we're right here. So what is the opposite side? Opposite side is that one right there. So it is 1098.421 divided by
500.
the adjacent, which is 500.
Wow.
All right, so
What's phase angle useful for?
what's that?
What's phase angle useful for?
Okay, phase angle is really important because remember you have your sine waves. So that's voltage, and then this is amps. We want to know, does it look like this and follow it? Oh, that's terrible drawing, but does it follow it, or is it out of phase where it starts over here and this goes to 0 when that goes to peak and this goes down? You know, that's out of phase, right? So we want to know that. What is the angular difference between here and here? Follow?
Yeah, where do you draw your triangle on that?
Oh, why do I draw a triangle?
No, where do you, like, on those points, I'm not following that.
There is no such thing as this is not a triangular thing.
Right, so what's...
Okay, so good questions. Let me do this a little bit better so that it's not like I don't even know what the hell you're drawing. Let's just go over here and do this. I'm going to come up a little bit and over so that you can see it up high. All right, so if I can draw this somewhat nicely, that's not going to be nice. All right, so we'll just do here. This will be my 0 line if I do it right. All right, so there we have the voltage, right? And the voltage just is. So there we go. And then our circuit's inductive, right? So it's inductive circuit. So Eli the Iceman. What's going to come first? The voltage or the current? So it's going to be inductive. Everybody follows why it's inductive? We had more X of L than we did X of C. So that makes it inductive. So if it's inductive, the voltage leads the current. All right, so in a perfect world, it would start here, and of course current is not as much. So that's my 0 line. So it would be here, and then it would come across here. It would be a little bit less, and cross here, be a little bit more, come down. So that would be in a perfect world. That's in phase, right? When the current peaks, the voltage peaks. When it peaks here, it peaks here. When it crosses 0, it crosses together. So
what would be an example of the angle number if that is in phase?
what would be, say it again?
What would be the angle percentage when those two are in phase?
The angle's 0.
0, okay.
Okay, because here's 0. What is the difference in angular difference between where this crosses the 0 line and the voltage crosses the 0 line?
0.
Everybody follow?
Yeah.
That is absolutely perfect. Okay, but now we'll use red for, and so the voltage leads, so it peaks out. Well, let's just say that it starts here and it goes like this. Yeah, that's right. All right. Okay, so the 0 is now here, right? That's 0 where the voltage starts. How many degrees is this?
90.
90. So how far out of phase is my current now?
90.
Is it leading or lagging? It's kind of hard to say. If I really drew the whole thing out, all you would do is see a middle of it and go, I don't know if that's, but anyway, don't get hung up on that. So Yeah.
And the reason why the current started there is because it's a more inductive circuit.
Well, technically it didn't start there. I mean, it would kind of come like this, and it just goes sort of on. So it's just, I started it there.
Mm-hmm.
I could have started it there. But,
As far as like visually understanding the volts leading the current.
okay, we could do it that way. We could say, yes, in time,
Uh-huh.
it's time, boom, we start the circuit right there.
Right.
So voltage takes off. Woo!
Black line.
And black line. And here comes the current.
90 degrees.
90 degrees later.
Got it.
So now the current is 90 degrees late. So, and it keeps doing that. So when the voltage crosses 0, well, the amps peaked out. Well, that's just going to make this whole thing very inefficient, right? So you just told me that it's 90 degrees out of phase, yeah? Okay, well, if I redrew it, I don't know if I can use another color here that actually shows up, blue. What if I said, well, it's right about here. It starts. And it's kind of going, you know, more like, if I did it right, I guess it'd be over here. It'd be just a little bit late right there. Something like that. I don't know. But it started right here.
It's less inductive.
Okay. And so now what's the difference between this and this angle?
Less than 90.
Like
What was it, 10? Is it 15?
10,
Be like, shit, I don't know, Kevin, you're the worst freaking artist I've ever seen. I mean, anything.
You get a right angle square.
It's actually a 3-phase.
Yeah. All right. So I need to know, and this is what we just did a little bit ago, right? This is now I'm trying to, by accident, but on purpose, draw what we just did. And we need to know what is the difference between here and here. Yeah? Okay. Now the only way to do that, because of my poor drawing, would be, if I guess we had an oscilloscope and we superimposed the two, we could count the reticles. Yes. And we'd figure it out. Well, but we can't, huh? The rectum tangle?
Rectangles.
The rectum tangles. All right, but we can't do that. So we look at a triangle that represents the numbers that we have.
We use our values.
We just use the values. This triangle does not translate into the waveform. No way, shape, or form. They're just numbers. Okay, but we put the numbers, and it just so happens that it works out to be a right triangle. So, and it represents this angle right there. So that's how we get that. I hope that worked.
No matter what circuit we get, right, we'll always have these three values of the resistance, the X total, and Z, correct?
You will always get.
Or always get enough information to get.
You will always get 1, 2, 3, 4, 5 pieces of information.
Okay.
We're gonna get this one circuit, it's like go wild.
What you do is up to you, because we were, of all this, we were given the 500, so you'll always have the 500.
Right, but you'll be given enough information to get
Yeah.
the rest of the values.
So, all right, so back here we decided to use tangent, which was 1098, 1098. So we're going to, but it's the arc tangent, so it's the second tangent, which is tan minus 1. Let me put that on here just so everybody's clear. So we decided to do tan minus 1 because it's the arc tangent. All right, so it's 1098.421 divided by 500, close those parentheses, equals
65.53 degrees.
all right, so that is technically the angle of theta equals 65.53 degrees. So back to my little drawing of what we did. I'll come back to the little drawing somewhere. I see it. There we go. This distance between right there and right there happens to be 65.53 degrees out of phase.
Can you explain a little bit about the arc tangent? And is there a regular tangent? Or
All right. So the difference between the regular tangent and the arc tangent. If I knew and I used to do this, but it just confuses people. If I knew that this angle right here, follow me, right there, look at the thing. If I knew that angle was 65.53 and I didn't know what Z was, I could use
Regular tangent.
I could use tangent to come up with that number.
Okay.
See, we're not doing that. We're going to use the arc because we know the numbers. We just need to find. So, and we chose tangent, arctangent, just because somebody yelled out, let's use arctangent. Well, we could do sine minus 1, which is opposite over hypotenuse. The opposite is 1098.421 divided by the hypotenuse, Z, which is 1206.87. We could have done that. Let's just try it. So second, sine minus 1 is 1098.421 divided by 1206.87, close parentheses, equals, so the angle of theta equals, what do you get? 65.53. Oh, that number sounds so familiar. It's right there. So we got the same answer. Or we could have done, instead of tangent or sine, we could have picked cosine. So cos minus 1 is the adjacent.
I'm sorry, before you continue, can you explain the 1098, the opposite? That's opposite of X.
Right there, 1098.
That's XT.
Doesn't matter. Doesn't matter if it is xt.
Uh-huh.
But let me just walk over here.
It's the opposite side.
I'm right here. This is me.
So regardless of SOHCAHTOA, we're always going to start from that.
This is the angle we want.
Oh, okay. If we
So
want,
that is always the opposite side. This is always the adjacent. That is always the hypotenuse from that point.
got it.
Because if you did it from this point, I can already tell you it's 90 degrees. Don't get that. This one right here, it's the opposite of that, so it's going to be 90 minus that.
And we're always going to be looking for that bottom right
That
corner?
right there.
Okay. Cool.
So, all right, so cosine is adjacent divided by hypotenuse. So the adjacent is 500 divided by hypotenuse, 1206.87. So the angle of theta is going to be probably about 65.53 because math works. Degrees. Yeah.
Earlier, there's a question about whether if xt was negative, if you'd use that. And I think you said no, but I think you want to use it if it's negative so that you know that the current leads the voltage.
Ah, that's a good point.
Capacitive circuit.
So if you, okay, yes. If you did X, let me move over here. Let's do this. So if you had your triangle, well, let's throw out some numbers. We had X of L equals, we'll just say 1,000, right? Just make it some easy numbers. And X of C was 1,500. And R was 250. Everybody follow so far? Where did I get these numbers? I just made them up out of nothing. All right. And I draw, technically, I would start like this. And I would say, what is X of T? X of T equals
X of L minus X of C.
X of L minus X of C. So XT equals
Negative 500.
-500. So technically, I would come down here because it's negative, which is in the X of C territory. This is the X of L territory. And it would look like this. So this number becomes -500. This is 250. And then X of, Z becomes, well, if you remember, Z equals the square root of -500, that's going to be the funny part, squared times 250 squared. I did it backwards, but so that's going to get rid of the negative.
When we draw that, the line and the line in the middle, the XL is always it's positive.
It doesn't matter.
Okay.
Nobody cares.
Right.
You could have done it up. You could have done it down.
Got it.
Yeah, for the negative 2, right?
So I'm worried that that might confuse people.
That's just to draw a representation.
It is. I don't actually do it. I prefer just to do it just a regular triangle and just put, x of c equals. It just makes more sense to me. I think the where I was headed with this is x of c is a negative number. So
But you say leave it nominal or something?
it's going to work itself out over here because you're going to square it. So it's going to turn into a positive number anyway.
Okay.
So you're going to have a positive number. So.
You compute the angle's going to be negative instead of positive.
But it's the same number, right?
Let's say that in our prior, our earlier example, that x of t was minus 1,098.
Okay.
Then your theta would end up being minus 65 degrees, showing that the voltage lag current is
Okay.
the opposite of what an inductive circuit would have.
Yes. Okay, so you guys can't hear him. Is a very good point. If this would have been a circuit, well, like I drew over here, back over here, and we ended up with a x of c because it went negative. Everybody follows me so far? All right. Then we're going to get z. Anybody do z for me yet? What z ended up being?
Domain error.
What's that? Did somebody do z?
Yeah, I got a domain error.
Yeah, so not.
Yeah, it would not compute out.
Let's
Even
see.
if I took the end, I tried to do it step by step.
Sick, dude.
Okay, negative 250
It doesn't do the full calculation, it gives you a scientific notation on ours.
559.
All right, so get rid of the negative. So let me think. So,
I think you're putting it in as a square root of a negative.
You have to use parentheses.
yeah, you do. But it doesn't matter because here's the point: when you square a negative number, negative times a negative is a
Positive.
so it's going to end up being a positive. So and then you're going to take the square root of that. So what is 500 squared times 250? Yeah.
The purpose of my original question of if you make it like negative or make the absolute value is just you want your answer in degrees and positive or negative.
Yeah. So what's happening? Okay. So let me just. I think I had everybody on board until I did that.
Yeah. Yeah.
So throw it all out because I don't even put it in my notes because I knew this was going to happen. Let's go back over to here. I'm going with, I know how to do this. All right.
Got it.
If you would have gotten x of c, that as the triangle goes down technically, right?
Yeah.
But I told you I don't even do that because I don't care. And because I don't. Because it's just easier for me to right side up triangle. But if I knew that x of t was a negative number, how did I get x of t being a negative number?
It's more capacitive.
More capacitive. I just put that over here and go, it was more capacitive, and x of t, fantastic, it's a negative number. I'll put it right there. Good for me. When I get all the way down to here and I go, what is the angle of theta? I'm going to go, wow, it's negative 65.53, which simply tells me what I already knew. Eli the Iceman was, if it went negative, was it more capacitive or was it more inductive? More capacitive. So it's more capacitive. What leads? Current. What lags? Voltage. That's all I care about. And so I honestly don't even put the negative there. I just go, the angle is, because it's not a negative angle, the angle is 65.53. Then I could ask you, so it's 65.53, but which one leads? And you would say, current, because it's more capacitive.
Yeah.
Why are you asking me these stupid questions? It's so obvious.
I think I'm back on track.
For all of these person.
What's that?
I said for the actual problem, it's more inductive. So.
But this problem was more inductive, so that made it this. So technically this was a positive number. We don't care. It was still 65.53, but in the example we actually did for real, what comes first? Volts leads the current. Boom. And what's the angle? 65.53, because it's not a negative angle.
The only reason I brought it up is because it was in the worksheets that one of the examples turned out that way.
Oh, okay. This thing?
Yes.
Okay. Did I put the answers in Canvas for this?
Both in there,
Both? Okay.
the blank and the answer.
So I'll hand this out. And the reason why I have this is simply because so many classes said, don't you have any examples we could work with? And if you want them, I'll bring them in. You can have that. You don't turn it in. You don't get penalized for not doing it. Don't care. The answers are already in Canvas. So I don't need you to go to Canvas and write down what I told you and hand it in and go, can I make that, boys? All right, so whatever.
No, you went to Canvas.
So, all right, break time.
Great.